Here I'm going to present a presentation on the topic testing of materials from engineering material subject. And the topic we are going to discuss is non-destructive tests. Myself, M.Kiran Kumar, M.Tech, faculty, Government Polytechnic, Kataram. So the topics to be covered in this particular presentation are the list of the non-destructive tests to be conducted, starting with the first one, visual inspection. Second one, dye penetrant test. Third, magnetic particle test. Fourth, ultrasonic test. Fifth, radiographic test. So let us have an introduction about what is non-destructive testing now. So non-destructive testing, as the name indicates, without destructing a sample or a product, a sample specimen or a product, without destructing it, we'll be conducting the test so that the product can also be useful after conducting the test also. So let us have the definition. Non-destructive testing is the means to define and locate the flaws within a material or a product without destroying or defacing the original product. So it is a type of testing by which we can find out the flaws within the material or a product without destroying the original product. So we can conduct several non-destructive tests which do not change the mechanical and physical properties after conducting also. After conducting the non-destructive tests also, the product has same physical and mechanical properties before it has. So the major ways to locate flaws, defects, cracks, and discontinuities are the types of tests. Different types of non-destructive tests are available. So let us have a look over it. See the first one, visual inspection. Second one, dye penetrant test. Third one, magnetic particle detection test. Fourth one, ultrasonic test. Fifth one, radiographic test. So these are the 5 tests to be conducted as a part of non-destructive tests on a specimen to find out flaws, defects, cracks, discontinuities, etc. So let us start with the first one, visual inspection test. So as the name indicates, visual inspection. We shall observe the specimen visually by the naked eye for any surface cracks or defects. And in some cases, we may be using low power magnifying lens to find out the visually available surface defects, or the surface defects which are visible. So the visual inspection test can be conducted to find out the surface defects. And in the surface defects, what we can find out or what we can check. So the dimensional accuracy can be found out. Second one, weld penetration can be observed or visualized. Third, undercuts can also be visualized. So let us start with the other factors, surface defect at the welded joints and the surface cracks, porosity, etc. So these are the totally, let us see. So dimensional accuracy is the first one, weld penetration, undercuts, surface defects in welded joints, surface cracks, porosity, etc. So So that is the visual inspection test. So now we are moving onwards to the second type of test known as dye penetrant test. Dye penetrant test, otherwise known as liquid dye penetrant test. Why? Because we'll be using a liquid dye as the name indicates. Let us find out the process in the name. Liquid dye is penetrated into the workpiece where the surface cracks are available. So the surface crack through which the penetrant enters shows the defect clearly, defect or flaw. So liquid dye penetrant testing is one of the simple non-destructive tests that can be applied to the metal. So this dye penetrant test can be conducted to ferrous metals, non-ferrous metals, and non-magnetic metals also. So we can say that it is not limited to only ferrous metals. It can be also successfully applied to non-ferrous and non-magnetic materials. So coming to the stainless steel, what is the purpose of conducting the liquid dye penetrant test in stainless steel? Is in which we can find out the porosity and weld inclusions by conducting liquid dye penetrant test. So this can perform excellently, nothing but best suitable test for finding out porosity and weld inclusions in stainless steel products. So next, magnesium, aluminum, brass, and many other non-ferrous metals can also be tested using this particular liquid dye penetrant test. So what can be found out? So using liquid dye penetrant test, the surface openings can be detected. Porosity of the material can also be found out. Material or weld cracks, seams, nothing but joints, you can detect. Slag inclusions. So let us check what is the process of liquid dye penetrant test. So there are 6 basic steps to be conducted to successfully perform liquid dye penetrant test. So let us start with the first. So let us have the list of the basic steps and then we can elaborate. So the first one, surface preparation. Next, penetrant application. Third, removal of excess penetrant. Next, developing, inspection, cleaning. So the first step is surface preparation, in which we clean the surface from any dirt, grease, and etc. The second step, the penetrant is applied, liquid dye penetrant is applied. The third step, we remove the excess penetrant available on the surface. Fourth, a developer is applied to clearly show the flaws or cracks or defects available on that particular product. Next, fifth, we can inspect. Actual inspection starts at fifth step, then finally cleaning will be done. These are the 6 steps. Let us elaborate the steps each one by one. So let us start with the surface preparation. So contaminants such as the dirt, grease, scale, acid, etc. must be removed from the surface so that the liquid dye penetrant can freely enter and can show the defect available in the product. So here we will be using solid solvents. Okay, we will be using the solvents which are capable of removing the contaminants. The solvents used are the solvents used for cleaning the surfaces of the specimens are commonly acetone, isopropyl alcohol, methylene chloride, etc. So these are the solvents used to apply onto the surface to clean the surfaces from dirt, grease, and other contaminants. So the second step, penetrance application. So before going for the penetrance application, a penetrant should have some properties. A penetrant should have some properties. What are those? Let us have a look. It should have a high penetrating capability. A penetrant, which we are applying as a part of liquid dye penetrant test, should have high penetrating capability. Second, that penetrant should have high fluidity. Fluidity means easily it should having the fluidity property, it freely flows into the onto the crack or the part or the defect which it want to show. Low viscosity. The viscous or the low viscosity, a penetrant should have low viscosity so that it can easily flow into the discontinuity or gap or defect. Higher wettability. Higher wettability means it should be wet for more time. Besides these four qualities, it should be able to carry a dye. That is a very, very important property of a penetrant. So these are the 5 properties a penetrant should have. So now let us see the steps. The dye is applied either by dipping, immersing, pouring, spraying, or brushing. Nothing but the dye is applied onto the specimen by dipping that specimen, or immersing the specimen, or pouring that particular penetrant onto the specimen, or taking a spraying gun or a sprayer and spraying the dye. Nothing but spraying the dye penetrant onto the specimen, or using a brush, we can paint the penetrant on the crack or defect available or the surface of the workpiece. After the liquid penetrant with the dye has been applied to the surface, the next step is only the waiting, a waiting period. A certain waiting period is required depending upon the type of penetrant used and the type of material to be tested. So the waiting time can't be calculated, which depends upon the type of penetrant and the type of material to be tested. Next, after waiting period is completed, then the excess penetrant must be removed. So extreme care must be taken to remove the penetrant. If the penetrant available in the crack or defect is not removed, then there is no chance of clearly visibility of this particular flaw or defect. So next step is developing. After the excess penetrant has been removed, then the developer is applied in order to make the discontinuities readily visible or clearly visible. So developer is applied so that clearly visible defects are available. Next, inspection. Inspection can be done either in a normal light with visible type of dyes, either with a normal light with a visible type of dyes, or backlight or fluorescent black light with fluorescent dye penetrant. Nothing but visible type dyes, normal light, and backlight fluorescent dye penetrant. So 2 types of dyes, fluorescent dye penetrant and visible dye penetrant. Visible dye penetrant can be inspected in normal light, whereas fluorescent dye penetrant can only be inspected in backlight. The last step is cleaning the surface properly so that the product can be used as a regular product. So let us have an example. A section of the material with a surface breaking, for example, we are taking a surface break is available or the surface is broken of a particular workpiece which has a crack, so that is not visible to the naked eye. So then penetrant is applied to the surface. Penetrant is applied to the surface. Then excess penetrant is removed. Developer is applied for clearly visibility and rendering the crack visible. Then so this is the dye penetrant test, or otherwise known as a liquid dye penetrant test. So now we need to move to the next type of test known as magnetic particle detection test. This is the third test, magnetic particle detection test. So this particular test depends upon the flux generated or developed. Otherwise, the flux can also be called as forced lines. These will be generated within the test specimen. Okay, so magnetic particle inspection is based upon the magnetic lines of flux or force lines that can be generated within the test specimen. Magnetic particle testing is used for detecting the subsurface flaws in ferromagnetic materials and alloys. Not only surfaces, subsurfaces also can be checked, or the flaws can be detected, especially in the case of ferromagnetic materials and alloys. So the component or the specimen is magnetized to test. If there are no surface or subsurface defects, then the force lines or magnetic flux goes through the piece without any deviation. Goes through the piece to the workpiece without any deviation. If there is any defect or flaw, if there is any surface defect or flaw, then the magnetic lines of force or flux lines will create a small north-south hole area at the location of the surface defect. If a defect is present, the magnetic lines of force or flux lines will create a small north-south hole area at the location of surface defect. So the iron powder, which causes the iron powder used in the magnetic particle inspection to form around the surface defect. So there are two types of surface defects which can be detected. One is the defects which are parallel to the interface of the workpiece or specimen. The defects which are parallel to the interface of the workpiece or specimen. Second is the defects which are perpendicular to the interface or sides of the test specimen, parallel and perpendicular. So let us have a look over this particular diagram. A cylindrical workpiece having a flaw or a defect here, I have a crack. So the magnetic flux is generated, force lines or magnetic flux is generated in this particular form. And here we can clearly see the flux lines are straight in the surface on the surface where the defects are not available. But this is the subsurface where the defects are available, and the deviation from the straightness to the curved form at the particular flaw or defect. That is the difference from the previous diagram. So now let us have the diagram here in the case A. The current is passed and a magnetic flux is generated. This is the test specimen having the magnetic flux generated, and here we are able to see the defect. And the defect north-south round form is available. Coming to the B, here we are able to see a circular form O-ring type on the cylindrical workpiece. Here we are able to see a cylindrical workpiece. A magnetic flux is generated and a cylindrical form we are able to see here. So in order to check the test specimen fully, both the longitudinal and the perpendicular direct indications must be checked. Perpendicular indications are inspected by using a circular coil which has current flowing through it in one direction. In order to check a test specimen fully, both longitudinal and perpendicular indications must be checked. Second is one direction. Third is a circular coil will set up magnetic flux lines that travel through the test specimen longitudinally. Nothing but whatever the circular coil we are using to develop the magnetic flux lines that travel through the test specimen longitudinal direction. And the power used or the power required, power used in this magnetic principle or the power required for electromagnets is either DC or rectified AC, either DC or rectified AC, which produces a current which flows in only single direction. The power requirements are high amperage and low voltage and high amperage. So the major items inspected in welding are penetration, fusion, cracks, and slag inclusions. So that was the magnetic particle detection testing. So now we can move to the next test, fourth test known as ultrasonic testing. So what is ultrasonic testing? First we need to know what is ultrasonic waves. Ultrasonic waves are the waves, sound waves, which have the frequency beyond the audible range, that is greater than 20 kilohertz. So those are commonly known as ultrasonic or ultrasound waves. So in this type of testing, in this type of ultrasonic testing of metals, the frequencies between 0.5 and 10 megahertz are generally used. So internal defects of the materials or metals can be detected by observing the waves transmitted to the metal. So how we'll be observing the waves? So whenever the waves are passed through the metal, so if any flaws are available, in the metal, the waves will be reflected back, and those are observed in a cathode ray tube, CRT, cathode ray tube display. The presence of flaws can be indicated by monitoring the reflection of cathode ray tube. If we do not have any flaw, then that is also displayed in the CRT. So let us see how these ultrasonic waves are generated. Ultrasonic waves are produced by stimulating a piezoelectric crystal known as quartz into high frequency vibrations by electric impulses. We need to stimulate a piezoelectric crystal known as quartz into high energy vibrations by electric impulses. So piezoelectric crystal is one which generates vibrations with the application of alternating voltage and vice versa. So let us have a look over this particular diagram. Here let us see the ultrasonic testing. This is the specimen in the B case first. Probe with single crystal. So this is a probe and this is the workpiece, and the ultrasonic waves are passed in this direction having the arrow mark downwards. They will be reflecting back, coming down, and wherever the defects are available, So the defect echo, so let us, if the defect is available, these signals are sent to the CRT. This is a CRT display, and if defect is not available, they will be sent to the boundary echo. So this is the width of the component. So let us see the same case with the two crystals. If the probe uses two crystals or quartz, then the UV rays pass through the workpiece, reflect back towards the other crystal, passing through one crystal and reflecting towards other crystal, and then it will be displayed onto the CRT, where we can find out the defect echo. So let us start. So a probe containing quartz piezoelectric crystal is coupled to pulse generator and single amplifier, which is placed against the component being tested. Nothing but which is placed touching or in contact with the workpiece or specimen. Close contact between the crystal face and the component can be achieved by a film of oil, a oil film. This ensures better transmission of the waves to the component. In order to transmit the waves properly, the oil film is required. So the waves are initiated at one face of the component. The waves are initiated at one face of the component and reflected back when they reach any air gap or a defect, or when they reach opposite face. So the reflected waves oscillate the crystal and hence produces electrical impulses. So whenever the rays are reflected, waves are reflected, they oscillate the crystal, nothing but the probe, and hence produces electrical impulses. Then in turn, these impulses are fed into the CRT or cathode ray tube. If any defects are not present, nothing but in the absence of defect, or the ultrasonic waves are uninterrupted the component and are reflected from the other side. Then they return to the probe and this will be displayed on the CRT as a boundary echo, as a boundary echo. So the CRT also records the entry of the waves into the component as a transmitter signal. The distance between this transmitter signal and the boundary echo gives the width of the component. When there is a defect in the path of the wave, some of the signal is reflected having a shorter distance to the travel, which appears on the CRT before the boundary echo. So the depth of the defect below the surface can be checked from its position relative to the transmitter and boundary indications. Separate transmit and received crystals, transmit and receive crystals mounted on the one probe can be used. Coming to the applications where we need to apply this particular ultrasonic testing. We can apply this for checking the internal flaws in the large sized forgings or large sized forged components. So for locating the minute internal flaws or defects in large forgings, ultrasonic testing is preferably suitable. So it can be also applied to the locomotives, nothing but rail engines and the components of the rail engines. And other products include wheel pins for fatigue cracks, etc. So this completes our ultrasonic testing procedure. Now we need to move to the last type of test known as radiography test. Coming to the radiography test, this test is also conducted to find out the internal defects in welded products and the same internal defects in castings and forgings. What is the principle? It uses the principle of radiation of short wavelength for detecting the internal flaws. Nothing but some radiation, some waves are sent onto the workpiece short wavelength is sent to the workpiece, which detects the internal flaws. So radiography test employs X-rays, gamma rays to detect these flaws. Nothing but we can use X-ray testing and we can use gamma ray testing also, depending upon the type of defect and the type of the specimen. So let us go to the work principle or the testing, radiography testing principle. These rays penetrates to the solid material. What are the radiography rays? These rays penetrates to the solid material. During transmission through the material, some of the rays are absorbed and absorption increases with the density. This can be detected on photographic film placed on the side of the material opposite to the source of rays. So a photographic film captures the defects. So let us have a look in this particular diagram. This is a film, photographic film on which the capturing will be done. And this is the X-ray source. And so this is the film and this is the plate or a product. If this is a glass pore or this is a defect. So some of the rays are absorbed. Fewer rays absorbed, hence a greater intensity over this area. So this is one, and let us have a look. This is a metal with a slag. These are the slag portions. So this is the photographic film on which these images are found out. This is the photographic film obtained with metals with blowholes. These are the blowholes. This is the specimen. And the last one is a perfect material or a metal without any defects. So where the X-rays are not absorbed. Here these are absorbed onto the metal absorbed. But here in the perfect material, without any defect, the X-rays or gamma rays are not at all absorbed. Let us start with the X-rays. X-rays are produced in a suitable vacuum tube. The X-rays having shorter wavelengths can penetrate effectively into the metals. A casted or a welded product is placed between the source of X-ray and the photographic film. During the transfer of the X-rays through a casting, some of the radiation is absorbed. The absorption increases with the density of the materials. And if it passes through an internal hole or crack, more rays reach the film and a dark spot results. If it passes through an inclusion, the absorption is greater, fewer rays reach the film and a light spot results. Since radiography is a two-dimensional, proper evaluation of the film intensity reveals the size and nature of the defect. Second type is gamma ray radiography. As the name indicates, gamma rays are produced in this particular radiography test to conduct the test. Gamma rays are produced by the disintegration of the radioactive material such as radium. So with the disintegration of the radium, gamma rays are produced. These rays are passed on to the workpiece, which check or which detects the defect. So the gamma ray radiography technique is similar to the X-ray radiography technique. So here we are able to see this is the specimen, this is the film, this is a flaw available. From a radioactive source, gamma rays are sent, the arrow marks downwards. This is the film view where the shadow of that particular specimen is fallen. So these gamma rays penetrates through solid material. During transmission to the material, some of the rays are absorbed and absorption increases with density. This is the same factor as in the case of X-ray testing. This can be detected on a photographic film placed on the side of the material opposite to the source of rays. Gamma rays are of shorter wavelength than X-rays. So they easily or efficiently penetrate into the metal. In this operation, the object must be placed at a definite distance from the source with a photographic film behind the object. Nothing but a photographic film should be arranged behind the object so to capture the picture. This method do not require any electric power and water cooling. It is suitable for small and more complex jobs. It is also suitable for higher thickened or high thickness jobs. So radioactive isotopes used in gamma rays are listed. First one, cesium-137, cobalt-60, iridium-192, samarium-153. So these are the non-destructive tests discussed in this particular presentation. So let us have a summary of the topics covered in this particular presentation. So here we have started with what is non-destructive testing without destructing the component. After conducting the test also, we can use the component as previous. So we have discussed about what are the tests to be conducted, starting with the visual inspection, in which we can visually observe the defect. And second is a dye penetrant test known as liquid dye penetrant test. Here a liquid dye penetrant is applied onto the surface of the workpiece. If a crack or defect is available, the dye penetrant enters and the developer clearly shows the defect. So coming to the 6 basic steps available in this particular process are surface preparation, penetrant application, removal of excess penetrant, developing the or using a developer, inspecting the component and cleaning the surface. So these are the 6 steps available for conducting the dye penetrant test. Third one, next test we discussed is magnetic particle detection test, in which the magnetic flux is generated within the specimen. The magnetic flux passes through the specimen, the straight lines. If any defect is present through the surface or subsurface, the magnetic flux lines deviate and form a small north-south hole area around the defect. So that was the magnetic particle testing. Next, we have discussed about ultrasonic testing, where ultrasonic waves are passed onto the workpieces or specimens. First, how to generate the ultrasonic waves were studied using a piezoelectric crystal, and later how to conduct it with single probe and double probe we have studied. Later, we have entered into the radiography test. So which can also locate the internal defects and welded products, etc. So in this, we have studied about 2 tests, X-ray and gamma ray testing. So these were the topics totally covered in this particular presentation. Thank you.